Okay, guys, let's keep talking about integration. So, if you might have noticed there's already homework posted on Canvas, and we'll have quiz 1 on February 10th. Yeah, I think that's the right date. Again, posted on Canvas, just double check the date. Um, the remote students, well, not remote students. Now there's two types of remote students. So we will do it during class. So we will do the quiz first and then we'll continue with lecture. And the master students, please attend class just for that day. So you can take the quiz and then leave. Um, this is for the master students who are not registered for the live class. All right. Okay. Any questions? Just like we did last term, the quiz will be open notes, open book, but no internet, no interacting with anybody else. All right, and you'll have to use your webcams. Okay, so today we'll do many more examples with integration, and hopefully it'll become almost second nature to you. So this is what we started with last time. If we are, yes, let me all right, last time we started with looking at, for a nice rectangular shape, what are the moments of inertia, Ix and Iy? And this is the only thing you need to know, all right? If you know this, you can basically work through the steps. That's relatively easy. So we just wrote down the formula for Ix, the integral, put down the correct limits that span my whole rectangle, and we got what we expected to get, bh cubed over 12. You do it for the other axis, Iy, you will get hb cubed over 12. This is analytically done. There's no numerical integration here. If for some reason you had to do this numerically, for instance, you don't have a nice rectangle, but a potato shape, okay? Then it's not possible to specify these nice limits. In that case, you have no other choice but to do it numerically. So let's look at how you do it for a nice rectangular shape first, and then we'll draw a potato. So if you have the same nice rectangle, to do integration numerically, remember what we do for one-dimensional curves. We slice it up into sub-intervals. We do the same thing, but in 2 dimensions. We slice this object up into sub-intervals vertically as well as horizontally. And if we say this is h height, and this is, let's say this is the base, then let's look at how many divisions we have made. 1, 2, 3, 4, 5, 6, 7, 8. So each of the, let's call this the x-axis on the horizontal. This will be delta x equal b over 8. Same thing we do in the vertical direction, 1, 2, 3, 4, 5. So each of my delta y will be h over 5. Okay, and so that's the first step. So the first step is always, whenever you're talking numerical, first step is discretize the object. And once you've done that, the second step is discretize the integral. So let's say if we were trying to compute, okay, let me just write second step. discretize the integral. So the original, if we were computing Ix, the full continuous integral is y squared dx dy. And if you remember, the way we discretize it is just, we have to correctly change the integral signs into summations. So we'll have two summations instead of these two integral signs. So we get this, when we discretize, we get Ix equal, there will be two sums, okay? And okay, all right, so let's think about what we should write here. What should we write for y squared? Maybe before that, let's think about what this summation means. So the summation just means we take each square box one at a time, square or rectangular box, one at a time, compute the insides for that box, do it for box number 2, box number 3, and etc. for all of them. And then we basically sum it up in the x direction and in the y direction. That's all we have to do. So when you write these sums in the x direction, we usually write I goes from, we say box number 1 in the x direction is I equal 1 to, let's say box number 1, 2, 3, 4, 5, 6, 7, 8. So I goes from 1 to 8. Same thing in the j direction. J goes from 1, 2, 3, 4, 5, 1 to 5. So the reason we use these two indices, and you don't have to use I and j, you can use L, M, and whatever you want. Most frequently we use I and j. What does this I and j help you do? If I ask you what's the address of this box, what do you say? Give me the address of that box, the one I just marked here. Just give me in terms of indices, not necessarily x and y locations. So in terms of I and j.
I5, J3.
Okay, let's see. 1, 2, 3, 4, 5. Yeah, perfect. So 5 and j is 1, 2, 3. So if you tell me I'm dealing with box number 5, 3, you have told me exactly which box you're talking about. Okay. So these indices basically help us write down the address of all the individual boxes. Okay, so two sums, I, j. So I will go from 1 to 8, and j will go from 1 to 5. That's all this means. All right. Now you tell me, what should we replace y squared with? Remember, we are not continuous anymore, we are discrete. Y squared basically is asking us, if you think in terms of continuous integration, what is this telling us? At a given location, what is the value of y squared? Okay, so think in terms of boxes. What box am I talking about? A particular one, all of them? Okay, maybe let me...
it's the value of y at each box.
Okay, yeah, it will be the y for each individual box. So we basically have to compute y squared in each of these boxes. How do we write y for box number 1? We can write y1 comma 1, correct? Box number 2 here is y2 comma 1. This is y1 comma 2, the one on top here. This would be what? Y1 comma 5, correct? So this would be, if you write y value here, it'll be y1 comma 5. Okay. So for any arbitrary box in here, what would you say? Y what comma what? That's what you put in here.
Yij.
Does that make sense? So basically, we have to compute y in each of the I comma j's. The ij values are given here. And dx becomes delta x, dy becomes delta y. All right. Now, in case this still looks a bit abstract, let me expand it out and write just a few terms. So when you expand this summation, is basically y1 comma 1 whole squared times delta x times delta y plus. Okay, so first we run through the interior. So j goes from 1 to 5. So y.
Professor, why don't you just take the delta x and delta yi since it's uniform?
Yeah, I actually wanted to make it a bit more explicit. So you see immediately that this becomes common. But yeah, you're right. I can just keep it outside a bracket. So you hold y at I equal 1 and j, you run through all 1 through 5. So 1 comma 2 whole squared. And just like you said, you see delta x, delta y are common to all of them. Plus dot, dot, dot. Once you reach y1 comma 5, all of the first row has been counted. Then you go to the second row and do the same. So once you hit the second row, it will become y2 comma 1 whole squared dx dy plus dot, dot, dot. And at the very end, you will end up with y, what is this? 8 comma 5. 8 comma 5 whole squared dx dy. So this nice summation expands out into many, many terms, 40 terms, 8 times 5. And I mean, you'd write a program to do this. You wouldn't do this on paper. Conceptually, does it make sense? What happened? Remote students, anybody has any confusion, please tell me. First time you see this, it can be a little dicey. So tell me now. And I'll explain again. Everybody understands this? You will do this on the quiz, on your own? All right, okay. Right? No problem. Okay, so here, you don't need to do this, right? Computing this integral using this discretization is not necessary because we can do it analytically. That's exactly what we did earlier, right? The previous class. But now let's take an irregular shape. And you obviously see all hulls are very irregular shape. They're never a nice rectangular cross section. So let's draw a potato. And so if we had an irregular shape, G, a potato, numerical integration is the only way. Unless, of course, you know the curve, the function describing the curve. But yeah, that's not easy. Numerical integration is our only option. Okay. I tell you so this potato's x-axis through the center of mass or center of area goes here. So this is the x-axis. All right. And then I ask you, how do you write Ix? What do you do? How would you start? What does this mean? Discretize the object. Is this making sense? I can't tell because I don't see you. How do you discretize this potato?
Do you like break it into boxes?
Yeah, you basically cut it up into, again, square boxes. Why square? Because we know how to compute the area of a square very easily. So it's basically delta x times delta y. Right? You could, of course, cut it into different shapes, but then this ease goes away. So let's cut this up into the same way we slice it up. Okay, and we do the same thing. We have this will be I equal 1, 2, 3. So this is 1, 1. I comma j is equal to 1, 1. For that guy, it's 1, 2, 3, 3, 1, etc. And now it becomes a bit difficult to write it as cleanly. I goes from 1 to 8, 1 to 5. Because you see, the first row here has 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes. The other ones have fewer or more. So you have to keep track of that. Another thing that you see happening is when I compute the area of this box, I will include stuff that's outside the potato. So that's, again, part of the error we make when we do numerical integration. But in essence, you would do the same thing. You would do a double integration over I and double over j. You'd have y squared I comma j delta xi delta yj. Why these? Because you might decide, okay, I don't want to cut everything uniformly. I will have different delta x and different delta y for each of the boxes. So once you put down I and j here, you're basically making it more general. Similarly, you can compute IY. Instead of y squared, you would have an x squared. All right, let's do several examples, and hopefully this becomes better and better. So let's actually talk about the centroid of an object. Is centroid of an object the same as center of mass of an object?
It is if the object is got homogeneous density and thickness.
Yeah, if only if the density is uniform throughout the object, you can say centroid is same as center of mass. But that may not necessarily always be the case, right? Let's say for this pen, the centroid would be somewhere, well, it would be the geometric center. But if I tell you this part is made of a very heavy metal and this part is made of very light plastic, you can obviously say, all right, the center of mass would be biased to this side, somewhere over here. So they do not coincide. But if you have the same density throughout, they would coincide. Okay. So for we will start with very general shapes and see how to compute their centroids, and then we will do specific examples. So let's draw an arbitrarily shaped curve. And we have f of x here. And first, let's try to compute the area under this curve. Okay. And if you understand these general forms, everything becomes super easy. So area, to compute the area, we would write it's a double integral of dA. This is element area of a small element. And in this case, it becomes double integral dx, dy. And this is the most general form you can write it in. If you start here, everything else is basically following simple steps. Okay, so area is, once we put down the limits, we have described our problem fully. So x goes from, let's say, 0 to L. Right, let's put down x goes from 0 to L. Inside we have just dx and dy. What does y go from? What's the limit on y for this problem?
F of L.
FL, yeah, it goes from 0 to f of, let me see, do I want to put down FL right now? Okay, no, let me put down f of x. Because you cannot put f of L here because that's only true when x equals L. For a general x location, it's still f of x. That's what this integration is doing, right? We're basically taking strips all over the place. So for any given general x location, we have f of x. Okay. So here, since we don't have a discontinuous function inside, we can basically swap the integral. So we go from x0 to L, y goes from 0 to f of x, dy dx.
Does it matter that it kind of looks like the y value is higher at f of L than anywhere else?
You're saying, does it matter that y here is larger than any other point?
Yeah, because that's like your upper limit, right?
No. Okay. All right. So, okay. No, that's not the case. So I could have, let me draw it on the side. So I could have had a sine wave, okay? And okay, well, sine wave is this. And this is x, this is y, and what do? You take a small cut. This is dx or delta x, and this height is f of x, okay? And the area of this strip is dA. dA is what? dx times f of x, okay? And how do you find the area over the whole thing? You would just, area of the whole thing is you integrate dA, okay? When you integrate dA, this becomes a single integral fx dx. X goes from 0 to whatever you want, 0 to L, let's say. So here you see at the very end, f of L is equal to 0. So it doesn't matter whether this is higher or lower. When you do the integration, it's automatically taken into account. Does that make sense?
Yes, thank you.
All right. So same thing we're doing here. Double integral of dA is basically you cut a strip, and the area of that strip is dA, and you integrate all the strips going from x equals 0 to L. That's the integral we're about to get here. So it goes from 0 to L. This dy is just y, goes from 0 to f of x dx is 0 to L f of x dx. So we recover exactly what we wanted. And I just want to show you that if you start from the very general form and simplify it, this becomes exactly what you expect intuitively. Fx dx is the area of this small cut. And when you add up all these small cuts, starting here, ending here, that's what the integral does. Okay, that's the area. If you have, let's say, a symmetric object like a hull, I think we did this, but it's good to just recap quickly. If you have a symmetric object, because we will deal with symmetric objects a lot. So for symmetric objects, we do the same exact thing. Area is integral x goes from 0 to L. And so one thing, let me go back 1 second and talk about one important thing. Why is it not possible to integrate in x first here? Why did we do the integration in y first? So we did this integral first. Why not the other way around? could have said we do the x integral first and we just get x goes from 0 to L, so L times whatever.
Because y is a function of x.
Yeah, does everybody get that? See, the y limit on y goes from 0 to f of x. Y depends on x. So we cannot evaluate the integral in dx before we evaluate this. We simplify out this guy first. Okay. Yeah, whenever you see one of the limits depends on one of the variables, that variable has to be kept for last. That variable is x in this case. So same thing here. Area goes from 0 to okay, and we say this curve is f of x. And you can see here y goes from and of course we have dy and dx here. Y goes from what to what? Our hull edges are the top curve here and the bottom curve here. What do you write the limits here? Okay, is this making sense? No, no. Tell me if it's not. Okay. All right. Okay, so what do you say? Y goes from what to what? X goes from 0 to L, that's obvious. That's the only thing we need to describe our insides of our object. But what about Y? Think about this strip. What's the height of this strip?
Would you go from negative f of x to f of x?
Yeah, you go from minus f of x to plus f of x. Okay, and when you do this, you have f goes 0 to L. Again, we integrate the y term first. So we get y minus f of x to f of x dx. So you get 2 times x equals 0 to L f of x dx. Which again should make sense intuitively. This integral just represents area of the top part. And since it's symmetric, the area of the full thing will just be 2 times that. All right. Now let's talk about centroid. Okay. Yeah. We will take the same thing, the same curve as here. Instead of computing the area, we'll compute the centroid in x and in y. Okay, so let's see. Remember, the centroid has 2 coordinates. Since we are dealing with a 2-dimensional object, it will have an x coordinate and a y coordinate. So for the general form of computing a centroid, x centroid is double integral x dA over double integral of dA. Okay, which is just double integral x dA over area. Area we already computed. We have that here, so let's leave that out. Let's think about the top part, the double integral of x dA. So numerator is dA, remember, dA breaks up into dx, dy, or dy, dx, whichever, doesn't matter. All right. Help me put down the limits. What are the limits now?
Zero to f of x.
Yeah, since we are talking about this enclosed area, we go from 0 to f of x. So 0 to f of x.
And 0 to L. Or not L.
Yeah, if I mark this L, this is 0 to L, right? Okay. So look, it's very similar to computing the area, but now we have an extra term. Instead of a constant 1, we have a variable x. But it doesn't matter. We just do the integration as always. Okay. All right. Again, since this y limit depends on x, we have to integrate in y first. So this becomes x goes from 0 to L, x, y goes from 0 to f of x, dx. Okay. And this simplifies to x, f of x, dx, 0 to L. Can we go further? Should I stop here or keep going? If I ask you to integrate this, can you do this?
Yes.
Okay. How do we proceed? What's the integral of x fx dx?
X squared over 2.
Do a substitution.
Okay, all right. So it's not x squared over 2 because f is not a constant. Okay. If this were a constant, yeah, it would be x squared over 2 times whatever the constant is. This is a function of x. We don't know what this looks like. I didn't tell you the curve looks like ax squared or so this could be whatever. This could be sine x. This could be x squared plus bx plus c. It could be exponential x. Okay, it could be whatever. But unless I tell you this looks like something, you don't know how to integrate this. Okay, does this make sense? We're talking about a very general curve. This f of x can take any shape, like the 3 I've written here. So we cannot go any further. We have to leave it like this. Hey, remember, never put x squared over 2. All right, you guys should revise your Calc 2 stuff because we will be doing this a lot. All right, then, okay, so we can't go any further, so let's put down, so x centroid becomes 0 to L x f of x dx over area. What is area? Area is here. F of x dx. Okay. Can we cancel stuff out?
Yeah, you could cancel the integral from 0 to L of f of x dx.
So we should cancel this guy, and this guy.
Yeah, and you just have the integral from 0 to L of x dx.
Okay, so never, ever do that.
Sorry.
Because this is not multiplication, right? This is not fx. So this is not 5 times 2 or something. This is saying you need to evaluate this integral to get what it looks like. This is an operation. So the operation on top and the bottom don't, yeah, you can't, you shouldn't cancel it out directly. So think about if I gave you some f of x, you would write x sine x dx. If I told you f of x is sine x over sine x dx, okay? So you don't just, don't cancel out the sine and the sine here because this will evaluate to over minus cosine x 0 to L. And the top part, it's, you have to do integration by parts. So you'll have 2 different terms. So can't cancel out. Okay. So this example, if you're given that f of x is equal to sine x, that's how we get the centroid in the x direction. We do the same exact thing for centroid in the y direction. Instead of xc, we do yc. Instead of x, we write y. Okay. Similarly, yc is double integral of y dA or double integral of dA. Denominator remains unchanged. We, again, don't need to compute that, but we do need to compute the y at the top. So numerator y dy dx. See, the only thing you have to figure out is what are the correct limits on x and y. Once you do that, then you're done. All right, let's look at our curve. What are the limits in x and y? Tell me, x goes from,
0 to L,
right, and y?
0 to f of x.
0 to f of x. Yeah, same as before. So y goes from 0 to f of x goes from 0 to L. The only thing that's different is instead of x, we have a y inside. All right. So remember, since this is a function of f of x, we need to integrate in y first. What do you get? What's the inside?
Y squared over 2.
Yeah, y squared over 2, 0 to f of x dx, which is 1/2 x goes from 0 to L, f of x whole squared dx. Okay, so that's basically it. Now we have our formula for yc. We have the numerator, we have the area from before. So yc is 1/2 of f of x squared dx, 0 to L. And this is 0 to L f of x dx. Remember, this is valid for any general form. You can plug in fx equals sine x, exponential x, or your hull shape. This never changes. This is a very general formula. There is a somewhat more intuitive way of doing this. Well, sometimes intuitive way. Okay. So another way of looking at this. So the other way of looking at this, if you recall, well, let me. If we have, let's say, 3 shapes, so one square here, one wonky shape here, and one strange hut here. So for first guy, looking at all of them individually, you see the center of masses will be at different locations. And if you know this is X centroid 1, Y centroid 1. This is X centroid 2, Y centroid 2. And this is X centroid 3, Y centroid 3. What is the composite? Recall that the composite centroid can be written as. Do you remember? What can we write? So these 3 things are glued together, and I ask you, give me the composite. So give me the composite centroid that might be here. What's the value of this composite XCYC? Okay. Can you tell me what XC can be written as? I also give you the area of the first guy is A1, this is A2, and the other one is A3. How do you write this? X equal what? Think about the center of mass. How do you compute center of mass? If I gave you mass of the first guy, center of mass of first guy, mass of second guy, center of mass of second guy, etc. How do you compute the composite center of mass? You've done
Isn't it
this.
like the summation?
Okay, yeah, summation. So what's the first term we can write?
XC1 plus XC, is that 2? Or
XC1 times area 1, okay? And then the same for the others, XC2, area 2, plus XC3, area 3. And divide all of them by
3? No.
the total area. Okay. And you see the units are consistent. The top is meter times area, which is meter cubed, and the bottom is all meter squared. So in the end, you end up with meter. So this is correct. If anything else would be a problem. You have to have meter on the left and on the right.
Yeah, that makes sense.
All right. So this you've probably you've seen in other classes. You do the same for YC. So Y centroid is YC1, area 1. And divided by the sum of all the areas. Okay. So you've seen this before. Now, the integrals that we wrote are the same thing, but written in continuous form. Let's take a look at the integrals we wrote. Does this look very similar to this guy?
Yes.
Okay, tell me why. Let's go with the easier one, the denominator. Why does double integral dA represent the same thing as here?
It's the total area.
It's the total area. If you have an infinite number of small cuts, you take the area of each cut and add it up. Here, this is not infinitesimally small. These are huge objects. Okay, but in essence, it's the same exact thing. The numerator, if you look at it, it's also the same thing. X times dA. If the area of this guy is dA1, that's exactly what this becomes. X times dA. Okay, same thing for y. Where is y? Okay, here, look. This integral is exactly the same as what's written here. Summation of dA is summation of areas. Summation of y times dA is summation of y times area. Okay, so conceptually, that's what this represents. Okay, if you understand this, you just have to be able to translate from here to there. All right. So we talked about Y centroid. Okay. All right. All right. Okay. 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 All right. So we talked about the centroid of this guy here. Let's talk about the centroid of a symmetric hull shape. So for a symmetric shape, without doing any computation, can you tell me one of the centroids of this guy? Either XC or YC? Is it obvious?
It's obvious.
Yeah.
It's going to be along the the y equals 0 axis, and it's going to be at L over 2 on the x-axis.
All right. I agree with the first part, not with the second part. So you can see the Y centroid has to lie on this axis. So YC is equal to 0 for sure, because it's perfectly symmetric. The XC is more complicated. It depends on what this f of x looks like. So this is not a perfect rectangle. Okay? If it were, you would say, all right, midpoint, midway through. But since this is an arbitrary shape, we have to resort to the integral, either analytically or numerically. So yeah, for anytime you see a symmetric shape, one of the coordinates becomes obvious. Y centroid has to lie on this line. So intuitively, we can tell that y centroid is 0. Okay, x centroid we don't know, so we have to compute it. And if ever you're in doubt, you can of course do the full integral. So analytically, just to show that the integral indeed gives us 0, we have y centroid is x goes from 0 to L, y goes from, this time it goes from negative ffx to plus fx. So negative fx to plus fx. And inside we have y dx or dy dx. Divide this by area. So this is the same formula that we had written earlier. Okay, let's evaluate this very quickly. So this gives us yc is 0 to L. Inside we get y squared over 2 minus fx plus fx dx. And you see the top is 0. Okay, just to convince you that the formulas we have are consistent with what you expect to get. And for x centroid, you can do the integral. It will not come out to be 0. It will come out to be some non-zero value. We expect it to be somewhere here. All good?
Yep.
Okay, let's do some specific examples with a known fx, like a straight line or something simple. So let's do this example. Right, this is obviously a rectangle. You know how to compute the area. It's half times base times height, or half L times B. But just to show you that the integral will give us the same thing. So area is what? Area is 0, x equals 0 to L fx dx. Okay. Instead of fx, what do we write?
B over L times X.
Yeah, our fx is given to us, b times x over L. So we have 0 to L bx over L dx. B is constant, L is constant, so we just get b over L x squared over 2, 0 to L b over L times L squared over 2, which is half base times height. Oh, sorry. Okay, so that's it. That's if this were not a straight line, but any weird shape, you do the same exact thing. You just have to know what fx looks like. If we want to compute the x centroid here, so x centroid, we compute x fx dx 0 to L over area. All right, what do we write inside? Dx remains the same, but we have to simplify this guy. What do we write? It's just multiplication, x times f of x.
X squared times b over L.
Yeah, we just multiply x times f of x again, given to us here. So is b over L times x squared. BL constant, so easy to integrate. So this becomes b over L x cubed over 3, 0 to L over area. So is b over L cubed over 3 over half b times L. That gives us a 2. This is gone. And yeah, this cancels that guy. Two L over 3. What is that saying? Does this number look familiar? Centroid of triangle is 2L over 3. What is this saying?
That the x component of the centroid is like a third away from the end.
Yeah, from the this axis, our x centroid location is 2/3 of the way, so somewhere over here. Okay, somewhere on this line lies our centroid, and we would do the same for the y. Okay, it turns out it'll be b over 3. So here, so that's where our centroid will lie. Okay, so and again, we can very quickly compute this. So yc is integral of fx squared over 2 dx 0 to L. Remember, when you compute yc, it becomes an fx squared over 2. Let me go back 1 second. The starting formula looks the same, okay? X dA and y dA. This is a double integral. Once we've simplified this to a single integral, the formulas don't look the same. This is f squared over 2. For x, it was just x times fx. Now we have fx squared over 2. So don't mix those up. So we evaluate this guy divided by area. Yes, yes, yeah, okay. So we have half of 0 to L bx over L whole squared dx. over area. Okay, this is very easy. So half b squared over L squared. X squared dx gives us x cubed over 3, 0 to L. Area is half b times L. B squared L over 3 half b times L. B over 3. Okay, so that's the y location of the centroid, b over 3. 2L over 3 and b over 3. Okay, we've talked about area, we've talked about centroid. Now let's talk about moment of inertia, area moment of inertia. So we can also compute area moment of inertia. Remember, we used the formula once. Ix is y squared dA. Iy is x squared dA. We basically do the same for this example. Okay, Ix becomes I just put down the limits. X goes from 0 to L, y goes from 0 to f of x. What do I do next? What's the next step?
Do you replace y with f of x?
Yeah, you can do that. So in this case, y is just f of x. So before we do that, let's break this dA up into what? So this guy is what?
dx and dy.
Yeah, it's dy times dx. Okay. And you see now we have an integral in y. We have a y squared dy. So we can evaluate that very easily. It's basically the x remains untouched, and when we do y squared, it becomes y cubed over 3 from 0 to f of x dx. And now we basically have it in terms of f of x, like you were saying. So 0 to L, 1 over 3 f cubed of x dx. Okay, what next?
Replace f cubed of x with bx over L cubed.
Yeah, exactly. So f of x, we know for this problem looks like bx over L. So we replace that 0 to L, 1/3 bx over L whole cubed dx. And we see everything is a constant except for x. So this is easy to integrate. So it's b cubed over 3L cubed. And the integral is x to the 4 over 4, 0 to L. Okay, so it's b cubed over 3L cubed, L to the 4 over 4. Which is 1/12 L b cubed. What does this represent? LB cubed over 12, area moment of inertia x. Intuitively, what should you always think of? What does this mean? So area is obvious, centroid is obvious, but what about the intuition for Ix? What does that mean? Think about this thing hitting you in certain scenarios. Okay, moment of inertia, we talk about what? Translation, something else, things moving in a straight line or something else.
Or rotating.
Yeah, we talk about, whenever we talk about moments of inertia, we talk about things rotating. So if this is, let's say, a flap of plastic, that's a rectangle, that's a triangle, and this is rotating about this axis, okay? So you're just spinning about this axis. And is it more difficult to spin about that axis or that axis? Intuitively, what do you say? Is it more difficult to spin about this axis or that axis? Or if you think of it another way, if this thing is spinning and it hits you in the face, would you rather it hit you in the face while it's spinning about this axis or spinning about that axis? Which one, x-axis or y-axis?
X-axis.
Yeah, you'd rather it hit you when it's spinning about the x-axis. It will hurt less, okay? So moment of inertia about the x-axis is smaller compared to moment of inertia about the y-axis. That's all this means, okay? Another way is, how is the area distributed? How far away from the spinning axis is it distributed? So, most of it is close by to my axis. A little bit of it is farther away. But when we talk about this axis, there's almost nothing close to us. Everything is far away. So moment of inertia is very large when computing about y compared to this axis. Okay? So intuitively, always think intuitively, what do these things mean? Centroid, we know, area, of course. So area moment of inertia. Always think about the thing hitting you while it's spinning. All right. So Ix gives us this. And remember, Ix means the thing is spinning about the x-axis. Iy, we can compute just like we did here. So Iy is 0 to L. Y goes from 0 to fx. x squared dA. dA. Okay, and just like here, dA becomes dx times dy, dy times dx, same thing. Okay, and again, to get you into the habit, which one do we evaluate first? Dx or dy? The x integral or the y integral?
The x?
You say we evaluate the dx first because there's an x squared? Remember, always look at the limits. You see the limits for x constant, constant. Limit for y not the same. The lower limit is a constant, upper limit depends on x. So we need to resolve that guy first, okay? So we need to leave x alone and we need to resolve y goes from 0 to fx. Well, x squared you can put here and dy dx. So we need to resolve this integral first. Okay, so this just becomes integral of x squared fx dx. X goes from 0 to L. Now it's a one-dimensional integral. What do we write? What goes inside here? So dx remains the same. What about the inside?
Plug in the function.
Yeah, it's just x squared times fx. So it'll be x squared times fx. What is fx? It's bx over L. Okay, so this one's easier to do. So we have b and L constant, 0 to L x cubed dx, which is b over L, x to the 4 over 4. Okay, so we get bl cubed over 4. Yes, let me check. Yes, bl cubed over 4. And if you compare this number to this number, you already see there's a 1/12 here. There's only a 1/4. There's an L cubed here. If L is very long, then you see this number will be much larger than the other one. If L is larger than B, okay? So the number matches our expectation. All right, so please review this. All of this is very essential for building up on the concepts. None of this is difficult. All you have to know is we start here, we plug in the correct limits, and then just keep evaluating. That's it. Okay. So the only thing you have to know is the starting point. All of this we have been doing analytically because we know these nice functions. If we were to do this with a potato, how would you do this? So you cannot solve this analytically. How would you do it?
Numerically.
Yeah, you do the same numerical summation that we talked about previously. Okay, and we'll do more examples. But you should, from everything we've talked about, you should be able to convert this into a summation that's for a numerical integration. All right, any questions? Okay, then in the homework you have to do this numerically. So please take a look and ask me next class. Whenever some things will not make sense because this is probably one of the first times you've done this in detail. So write down things that don't make sense and we'll go over it in class together. So please bring questions. Okay, and if there are no more questions, then I'll see you next class.
Thank you.
Right, okay, bye.
Yeah, have a good one.